that I've been working on with my supervisor, Alex, at Cornell, and my colleague, Matt, who's a PhD student, who gave a wonderful talk yesterday about all the stuff he's doing related to spectral computations for operators. So this is in that flavor. I'm going to give a little bit of a different perspective that emphasizes some of the gains we see when we're working directly with differential operators and integral operators. So the sort of main character today is going to be an operator L, and the only real technical requirements we need on this for the top level theory to go through is that L be closed and densely defined on a Hilbert space. So we can work with unbounded operators, like differential operators in particular. Now, in practice, when we want to make this run on the computer, we're going to have to do some underlying approximations. And the technology that we have right now allows us to deal with things like variable coefficient differential operators, where the variable coefficients are smooth. And it also allows us to work with some interesting integral operators, where you might have a multiplicative part and integral part of the operator. I'll explain a little bit why we're looking at that form in a slide or two. So classically, if we have an operator and we want to do some computation with it, for example, we want to compute some eigenvalues and eigenfunctions of the operator. Really, since the modern computing era has come into its own, the standard strategy has been to discretize the operator equation to get a matrix equation, and then apply all of the wonderful algorithms we have for numerical linear algebra to compute the eigenvalues and eigenvectors of the matrix. And we hope that, in most cases, these eigenvalues and eigenvectors of the matrix will allow us to get some good approximations to the eigenvalues and eigenfunctions of the operator. So this is a great, there's no doubt about it, great paradigm. It works really well most of the time. But what I want to talk about today is when we start to think about more exotic spectral properties of the operator. So in particular, I'm going to talk about what happens when if we try to use this strategy to compute the spectral measure of an operator. So in case you're not familiar, I'll just first mention the matrix case. We say the spectral measure of a matrix A with respect to some vector is just a sum of Dirac deltas that are supported on the eigenvalues of the matrix A. And I've represented the Dirac deltas here just as these straight lines, and I've tuned their heights to be the height of these coefficients. And those coefficients are exactly, oh, sorry about this. This is exactly the projection of the vector v onto the corresponding eigenspace. So the kth eigenvalue has Dirac delta with height that's equal to the projection of the vector v onto that eigenspace. For an operator, if it has discrete spectrum, we again get the Dirac measures supported on the eigenvalues with the projections, this time of a function, onto that eigenspace. Sorry about the notational there. But in addition to the discrete spectrum, we can also have continuous bits in the spectrum. So today, I'm just going to focus on operators that have some discrete spectrum and possibly some absolutely continuous spectrum, so that there's a nice density function, which tells us about the measure on the continuous part of the spectrum.
So can I make sure I understand?
Yes.
The measure you're speaking of depends on the matrix or operator and on the vector you're applying.
Exactly. So in some of the related literature, like density of states, this would be called the weighted density of states with respect to a vector. And then if you want to get something more universal that doesn't depend on the vector, you would do an averaging procedure over a suitable basis. OK. So one might think, one might wonder, if we discretize the differential operator and compute the spectral measure of the matrix, how are we going to use this this discrete measure, the sum of Dirac deltas, to approximate the continuous part of the measure here? So you'll notice that the heights of these Dirac deltas are roughly following this profile of this continuous part of the measure. So this is to illustrate that often what we see in practice is that the eigenvalues of this matrix will cluster along the continuous spectrum of the operator. And that in the sense of measures, you may sometimes get convergence, so that if you look at the sum of these discrete measures, they may actually be converging in the limit to some continuous measure. So this is the principle behind most density of states calculations. So if you want to know a little bit more about this discretize and solve procedure for spectral measures of Hamiltonians in quantum mechanics, you can look at the thesis of Mayer and some of his early papers from the 80s. You can see pictures like this using discrete measures to approximate continuous measures. Something else, another improvement on this method, if you're uncomfortable with approximating continuous measures or even a nice density function with a sum of Diracs, you might think a reasonable strategy would be to discretize and smooth the measure of the matrix. So instead of taking the actual spectral measure of the matrix, which is a sum of Diracs, we replace the Diracs with some smooth approximation to the identity, like, for instance, suitably scaled Gaussian. And so each of these, this cluster of eigenvalues and the cluster of Diracs that results from it is replaced by a sum of smooth functions. And that gives you a continuous approximation. So there's two difficulties that come up with this. One is so all the issues that Matt spoke about yesterday, when you're trying to use discretizations or matrices to approximate spectrum of an operator, all those come over to those cases, because sitting under this measure is the ability to resolve the eigenvalues of the operator accurately. So that's one issue. Number two is it's quite difficult to understand how one should choose the discretization parameters and the smoothing parameter to accurately resolve this continuous function. So if you look at the Siam review paper by Lin Lin and Yusuf Saad and Chao Young, I believe, they mention this problem. They say usually the smoothing parameter is sort of an art form to choose that, and the physicists who do these calculations have a lot of experience and sort of an appreciative eye to tune these parameters properly to get some sensible density. So what I want to get into today is I'd like to suggest that maybe there's an alternative way to construct an approximation to this measure that allows us to approximate nice the density function itself, which is often continuous and smooth. So we're approximating a nice smooth function with a sequence of smooth functions instead of going to the matrix setting and trying to approximate this with a sum of discrete measures or sequence of discrete measures. Okay, so to motivate the approach we're going to take, I just want to take a quick detour into one of my favorite subjects, which is contour integral eigensolvers. So, appreciate Nick talked a little bit about this on Monday in the first master class. the Feast, if you recall, the Feast matrix eigensolver uses the resolvent of matrix A to compute spectral properties of A. In particular, Nick talked about why this Cauchy integral acts as a projection onto the eigenspace of the eigenvalues inside this contour, which you're integrating over. The details of the algorithm aren't too important. What I want to focus on is the fact that we're resolving spectral properties of A if we approximate this contour integral with the quadrature rule. All we need is a few samples of the resolvent on the contour in the complex plane. And from those samples, we can extract spectral information about A. OK, so this is the Feast algorithm. The details are not that important for our talk. More important is that one can do this same procedure, extracting spectral properties of an operator from samples of the resolvent along a suitable contour. And so it's basically as simple as plugging in your operator into your projector. And instead of applying the inverse of some matrix, we're applying the inverse of some operator. So in practice, you usually apply the shifted linear solves. You usually apply the inverse by solving shifted linear systems. So instead of solving shifted matrix equations, we're solving shifted linear differential equations or integral equations. So this is the sort of strategy that we're interested in because of two reasons. When the projector is applied adaptively, meaning we don't fix a discretization of L, but we actually adaptively resolve a solution to each of these when we apply the projector. At each quadrature node, we solve in ODE adaptively. And we're able to resolve the eigenvalues of the actual operator. And we're able to get around the usual difficulties of spectral pollution and some other sensitivity issues that come up when you're working with large spectral discretizations of differential operators. So working adaptively with the operator, instead of fixing a discretization size and running a matrix algorithm, actually allows us to ensure that we're resolving the spectrum of the operator instead of the spectrum of the underlying discretization. And that's why we're able to overcome things like spectral pollution. So because we're able to faithfully capture spectral properties of the operator from samples in the complex plane of the resolvent, we were wondering if we could do something similar to get at the continuous spectrum of the operator, if there was any present. So here's sort of the complex analysis bit of the talk. Just like Nick talked about, when we scalarize the resolvent, so we just take some inner products with some functions, we get a nice scalar analytic function, except at some singularities. Oh, one thing I should have mentioned right at the beginning is we're always talking about self-adjoint operators today, so that our spectrum is always lying on the real line. And we always have a nice spectral decomposition of the operator. So our operator may have some eigenvalues. Say this is a common setup, some eigenvalues on the negative real axis and a strip of continuous spectrum on the positive real axis. So what Feast does is looks at the poles of this scalar function, which is analytic except at its singularities, which are exactly the spectrum of the operator. In particular, the poles of this are the eigenvalues of L, and the residues are the projections of F onto the associated eigenspace. So this is really what's going on underneath a feast. It's building a projector onto the target eigenspace by using Cauchy's formula and discretizing with the quadrature rule. Okay, so this is getting at the poles of this function, but to think about continuous spectrum, we need to take more general types of singularities into account. So common situation is that we have a strip of continuous spectrum on the positive real axis, which corresponds to a branch cut in this scalar function. Corresponds to a branch cut in the resolvent, essentially. And just as with the case of the poles, the singularities here are hiding the spectral information about L, if you will. So when this guy is a branch cut, the discontinuity, the jump across the branch cut, is exactly the density function for the absolutely continuous spectrum. So this goes back into some early work by Stone back at the very beginning of last century. And another good resource, like Nick mentioned, is CATW for all this stuff. If you want to know anything about the resolvent of an operator, open CATW. And it's an experience, for sure. So this is what we're doing, right? We're recovering the spectral measure, the absolutely continuous part, in the form of the density, by looking at the jump in the resolvent across this branch cut. So I'm just going to suggest a really simple algorithm based on this, right? So I'm basically going to say fix epsilon. So we're going to say some fixed distance away the continuous spectrum and take samples of the resolvent by adaptively solving differential equations or integral equations, as the case may be. So just a note, because L is self-adjoint, we have conjugate symmetry in the resolvent in the upper and lower half planes, which allows us to express the jump in the resolvent just compactly in this form. So we just take the imaginary part. We only need to look at the resolvent in the upper half plane because of the symmetry. Okay, so here's the algorithm. We take a few points, some sample points along the real axis. We're going to fix epsilon, which is going to be our distance that we're going to move off the real axis. We're going to choose some suitable function. So usually this comes from the application at hand. And for each one of these nodes, for each one of these sample points, we're just going to solve this ODE to apply the resolvent at that node shifted off the real axis by a distance epsilon. And then we're going to compute the inner product of our solution back with F. So that's giving us a sample of this function before we've taken the limit epsilon to 0. OK, so what does this look like in practice? This was one of the first things we did when we got it. We just thought, OK, let's throw some operators in there and see what we get. So step one, right? Here we have essentially a beam equation. We're looking at functions on the whole real line that are smooth and square integrable. This is the potential function, Q. And I've just chosen some sort of wavy thing that looks interesting. So our algorithm says we should pick some distance off the real line, solve some ODEs, and then compute inner products. So I'll say how we do that in just a minute. And first, I just want to show you what we get when we try to do this. We get some really interesting behavior. So what is this plot showing? This plot is not showing what happens if we solve these ODEs adaptively. It's showing what happens if we fix epsilon and refine the discretization size for this ODE. So you notice things look pretty reasonable over here. All of these discretization sizes are giving us the same result. They agree well. But as we move over into the continuous spectrum, we see that the smaller discretization sizes are giving us something that looks like an instability or some sort of noise. But as we refine n, we are able to clamp down on something that looks sensible. So the idea is...
It's also continuous spectrum on the left plus unbounded state?
Yes, so the continuous spectrum is exactly from 0 to 10. So yes, so I haven't explained why the bound states show up here. I will talk about that in just a minute. So the continuous spectrum is really from here over. And here we're seeing some spikes. Hint, they're probably related to the eigenvalues. So this is giving an idea of what happens if we fix epsilon and refine n. This is sort of the picture that you see. So just a word on the numerics. The way we solve the ODEs, because we're solving ODEs on the real line, we basically just use a Fourier spectral method after mapping the real line to the unit circle. Because of the decay in our functions, everything works out nicely. It's fast, well-conditioned, and we can do it adaptively if we'd like to, monitoring the coefficients in our solution. I'll just mention a word. This is essentially equivalent to spectral method using an orthogonal basis on the real line, which I think Marcus is going to talk about maybe in the next talk. So stay tuned for that if you want to know more about the underlying basis functions here. In the second step, we just compute the inner products, which are integrals, with a Clenshaw-Curtis quadrature over the circle. Oh, actually, I'm sorry. Yeah. In this case, we actually just use trapezoid rule on the circle. We can do a couple different domains. So this ODE is posed on the real line, but we can also do ODEs posed on the half line. In that case, instead of using a Fourier spectral method, we map to the unit interval and use the ultraspherical spectral method, which my supervisor likes to call the non-periodic analog of Fourier spectral method. And then in that case, we use the Clenshaw-Curtis quadrature to compute the inner products. Okay. So I showed what happened if we fix epsilon and refine n. So here's another example. This one's an integral operator. Pretty simple, just a multiplicative part, and then a pretty easy kernel to integrate against. We solve these shifted equations with a simple collocation method. If we fix an epsilon and then solve the shifted linear equations adaptively and compute the inner products, these are the measures we get. As we refine epsilon and then adaptively solve, we see that we get something that looks like convergence to 0 off the continuous spectrum, which is from -1 to 1. Some density on the continuous spectrum, and then some spike sitting over here off the continuous spectrum. So again, I'll talk about that in just a minute. Here's what happens if I don't solve my equations adaptively. If I fix a discretization size and try to refine epsilon, I adjust my smoothing parameter, things seem to go well at first, but then at 10 to the -3, I've suddenly gone too far, and things become unstable on the continuous spectrum. So Matt mentioned this in his talk the other day. There's a careful interplay between the discretization size that you're using and how close you can get to the real line. If you get too close to the real line, you choose epsilon too small, you start to get too close to the clustered eigenvalues of the discretization. You start resolving the spectral measure of the discretization, which is a clustered sequence of Diracs, hence nonsense. instead of getting the actual spectral measure of the operator. That's why adjusting n and epsilon is so important. It's important to fix epsilon and refine n. The question that brings up is, well, when we're fixing epsilon, can we reason at all about the accuracy that we've achieved? How do we know if we're smoothing too much? How do we know how close we can get to the real axis? So this is this is sort of the second big formula that sits under all this. Again, going back to the work of Marshall Stone. Basically, what we have is that these samples, this slice of the resolvent we're taking right above the real axis, is equivalent to a convolution with the Poisson kernel. So when we convolve the measure with the Poisson kernel, we generate that slice of the resolvent that's a distance epsilon off the real axis. So when we look at the discrete and the continuous parts, we see that we're computing some smoothed approximations to the identity. So that explains the spikes we were seeing at the eigenvalues off the continuous spectrum. And we also see we're also getting a smooth version of the density, just a convolution with the Poisson kernel. So let me move a little bit quicker. So epsilon is a smoothing parameter, in short. So this is the big gain that we get from approximating a continuous function or some sort of reasonably nice density function. Instead of approximating with a series of discrete measures, we're approximating it with a sequence of smoothed functions. And because of that, we can actually start to get nice results about the error in our approximation, about the convergence to the measure with epsilon. So we have some local results, which tell us if the measure is absolutely continuous in a neighborhood of a point, and its Radon-Nikodym derivative is held or continuous, then we know that the error there is order epsilon to the Helder exponent. Unfortunately, convergence degrades as delta shrinks down. So if we're near a singular or a non-smooth point in our density. We can also ask, can we exploit additional smoothness in the density? So this only lets us get up to linear convergence, up to log factors. But we can also design rational kernels. So instead of working with a Poisson kernel with poles at +1 and -1 on the imaginary axis, we can design higher order rational kernels. Instead of taking just one sample at the resolvent per evaluation point, we have to take a few, and we take a weighted linear combination of them. So I'll just finish by showing what these guys look like. Here we have a convergence result, local convergence result that shows the increased approximation power. We also get L1 results with weaker conditions on the derivatives. And here you just see this borne out for one particular integral operator we looked at. So this is with the Poisson kernel. We get O epsilon convergence as we move to the real axis. And this is with order 2 kernel. We actually do slightly better than the quadratic improvement. And that's just because of, we believe, because of symmetries in the density. So with that, oh, I'm going the wrong way. I'll skip my last example and just sum up. The main idea, instead of trying to compute the spectral measure of an operator with a sequence of discrete measures, we're able to construct an approximation with a sequence of smooth measures. So we get an actual density function, which acts like probability density. And then we're also, we get smoothed approximations to the identity appearing at the eigenvalues. So I think with that, I'll close. Thanks.
Time for one question.
How does this procedure depend on the choice of the vector F?
Yeah. So So the main thing is it can change the complexity of the differential equations you're solving. So if you have some horrendous f, maybe that will hurt you when you're solving ODEs. Typically, where these are showing up in application is you're either choosing random functions and doing some averaging procedure over them. That's like density of states calculations. The other place that they show up is if you're doing scattering, you're looking at time evolution. Then similarly, you could take f to be sort of your initial curve, and then you're evolving that in time according to like an elliptic differential operator, for example. The spectral measure with respect to that initial condition is going to tell you about which frequencies are likely to propagate forward in time.